Greetings, my name is Alfredo Juarez,
I'm Joel Love.
Sam Guernsey.
and we are Group 3. We are presenting Lab 4 about fatigue. The purpose of this lab is to calculate the moment components to maintaining specific stress. This specific stress value is 33,500 psi, and we are performing the test using a rotating fatigue testing machine. The specimen that we got is a hollow tube which has an outside diameter of 0.371 inches. Also, the inside diameter is 0.2955 and it has a length of 26 inches.
And so, once we got our test specimen, what we did was we went to the lab and we used the XRF scanning machine. And we scanned our test specimen and we found it to be almost all iron with just a little bit of manganese. And from there, we actually we went and plugged those values into MATWeb, and we found it to be 80 or AISI 10006 cold drawn, and we suspect it to be cold drawn because the values of that just matched up better percentage wise, and the surface finish looks to be cold drawn. And so from there, what we did was we took our sample, put it in the fatigue testing machine that we have over in the lab. And what we did was we had to grind off a little bit of material here to make sure that it fit into the bearing end of the machine. And then what we did was we fixed the this other end. There's actually another piece, but there was a groove cut into it. And so what we did was we put that groove to be right at the edge of the collet. That way, that's where your piece would break. And so, obviously, with it being a groove, we have to have a stress concentration factor. And in order to get that, what we did was we took our outside diameter and then we subtracted the radius of the groove on each side. If you were to like take a cross section of it, there would be two separate grooves. So that's why we did that twice. And what we did after that was we just kind of labeled that in the math section as D groove. And so now we'll just let Joel get into that.
So, a couple days ago, we were first doing the calculations and setting up the experiment. I mistakenly used the wrong KT factor when doing this and created a moment that was just much too large for the piece that we have. And so we were told to go ahead and go through the math section as if we hadn't, because we had no more of those actual grooves on the piece. So the way we understood this experiment was that we were going to be given a stress, which in this case we chose 33.5 KSI, and that would be our max stress. So we know that the equation that, stress max equals stress nominal times our KT factor. So then we could, divide the max stress by the KT factor to achieve the stress that we want as our kind of our average stress. So the first thing we did in order to find this, like Sam said, was to take our outside diameter and divide it by the diameter of our groove, which the value it gave us puts us between the first and second curve in table A22-8. The second part of this was to take the radius of the groove and divide it by the diameter of the groove, which this put us at 0.06. And so when we cross-referenced those on A22-8, what that gave us was a KT factor of approximately 2.25. We had to do a little estimation there because of where the curves fall. Okay, so we took this, we divided our max stress by our KT factor. We came up with just shy of 14.9 KSI, which was the stress that we wanted to maintain. To backtrack a little bit, the table that we used was for a grooved round bar in bending. And we determined that even though we had a hollow steel tube, that you don't need a special case for that. However, there was a specific formula, we know that we could use the flexure formula, which is your stress equals MC over I. But we also know that C over I is equal to S, or the section modulus. So being that our overall goal was to create an equation that could be manipulated in such a way that we could immediately find the force that we needed based off of a moment arm, or create a moment arm based off of the force. Because when we took the weight of our bearing and the weight of our shaft, added them together, we come up with a minimum weight that can be used. And so what we did was we rearranged this equation after taking the section modulus. We had to be careful about how we came up with this, because it's very easy to take the outside diameter or the wrong diameter. So the section modulus is actually pi times the diameter of the groove to the fourth minus the inside diameter to the fourth divided by 32 times the diameter of the groove, right? So, I mean, when you calculate it, it's about 1.30 times 10 to the negative third inches to the third. But we basically turned two variables into one variable to make it easy to manipulate our equation, right? So when we plug in, when we rearrange our equations, basically what we get is we can get I called it L because we already have enough D's up here on the board between inside diameter, outside diameter, diameter of the groove. So we just call the length part of the moment arm L and the force part of the moment arm F. As you can see in these two equations, we have it set up so that if we input a force, we can automatically draw a length, and if we input a length into the equation, we can automatically draw out a force. Now, we already said that the very minimum weight that would be on our that would be set in the bearing before we added any weight would be about 2.441 pounds. And so we find that by multiplying the stress that we want to maintain times the section modulus and dividing it by the 2.441 pounds, we get a moment arm length of about 7.93 inches, which for us worked. And based off of this, if we wanted to use more weight and less bar, or less weight and more bar, we could easily plug them into this equation to get out whatever, we could basically set the weight based off the moment arm and set the moment arm based off the weight. So do I have any questions?